Okay, this is a question which on the surface you might think is about gravitational fields, etc., because we're dealing with Mars and the Earth, but actually it's from our energy resources topic, section 8. Okay, so we'll have a look at this just now. All right, we're asked to think about the intensity of solar radiation at the orbit of Mars, and we're asked to prove this value. Okay, how are we going to prove that? Well, most likely using the information they've given us here, which is that the distance from Mars to the Sun is 1.5 times the distance of Earth from the Sun. Okay, so we're looking at a greater distance. Hopefully, you remember that from our wave topic, the intensity goes with distance, 1 over distance squared. Okay, so the further away we are, the greater that distance value is going to be, and therefore the lower that intensity value, and it's going to be going with an r squared. All right, so therefore we've got double the distance is going to be a quarter the intensity. Okay, now we're looking at ratios. The intensity at the position of Mars, okay, divided by the intensity at the position of Earth is going to essentially involve a ratio of our distances. However, it's going to be inverted. Okay, you can see here that the Earth's intensity is going to be Earth's distance and Mars' distance is going to be flipped. Okay, and we're also going to have to square it. All right. Well, what does that mean? Well, the distance to Mars is 1.5 times the distance to Earth. So therefore, we've got a factor of 1 over 1.5, and we're squaring it, and we're left with 0.4. What do we then do with that 0.4? Well, we know the intensity at the Earth. Now, that's actually in your data booklet as the letter S. This is the intensity of the sun's radiation at the Earth's surface, and that is 1.36 times 10 to the 3, the solar constant. So if you stick your 0.4 in and multiply by our S, we're left with 604 watts per meter squared, which I think you'll agree is very much our 600 watts per meter squared. All right. This question here, 5b, a little trick to it, so let's have a look at what's going on here. We're assuming that Mars acts as a black body, and we're being asked to determine its mean surface temperature. And we'll start by using our Stefan-Boltzmann law, which is power is sigma AT to the 4, and intensity, which is power divided by area. So let me just get this up. I thought I'd flip that. Okay, we use intensity equal power over area to get the fact that really we're only interested in sigma times T to the 4. Okay, so temperature is going to be the fourth root of intensity divided by sigma. Hopefully no problems at that stage. Now the difficulty comes here is we've just proven a value of 600. And actually, I'll be honest with you, I put in the original value of 600 here. But there's a clever little trick here. You need to reduce your value of intensity by a factor of 4. And there's a reason for that. This is where we have to think about a black body, okay, that Mars absorbs as much as it emits. Well, remember, the area of Mars which actually is doing the absorbing is simply the area of a circle. So we have a sort of a 2D projection whereby the amount of energy picked up by a planet, a spherical planet, is equal to the intensity times an area, and that area is actually pi r squared. It's simply a circle with the same radius as that of the planet itself. So the area absorbing is pi r squared. The area emitting, however, is the surface area of the sphere, which is 4 times pi r squared. Okay, so what this means is that the emitted intensity is going to be 4 times smaller than the absorbed intensity, which means you've got 150 there. And therefore, your value is going to be slightly different. Now, as I say, I admit I didn't think of this when I was looking through this problem. And I was a little bit confused when I read the mark scheme, but actually it makes complete sense. It's the fact that when we're calculating intensities and energy absorbed by a planet, then really it's a 2D projection of the planet, and the maximum energy that can be picked up by that planet is simply pi r, depends on pi r squared. However, the energy emitted by a planet, okay, is going to go with the whole surface area because the whole surface is doing the emitting, and therefore there's a factor of 4 there. No worries if you didn't get that. It's a really tricky little point, which just kind of, which I think we can just chalk up to experience. Last one, okay, hopefully slightly more straightforward. We've got the atmosphere being made of carbon dioxide and has a pressure less than 1%. And we're actually asking, why is there basically no greenhouse effect on Mars? Well, if there's a low pressure, then that means there's a very low concentration of particles. Right? Low pressure means low density. It means there's very little material or substance doing any absorbing. Okay. Well, remember, in greenhouse effect, there we're looking at the effect of absorption and then re-radiation. Okay. So as a result, very little of the radiation which is emitted by Mars will be re-radiated to its surface, and therefore there will be very little greenhouse effect observed on this planet. Okay, like I said, this question here really annoys me because I can see how it could trip up people. It's a factor of 4, which will count towards your answers, but really don't stress about it. It's a trick of geometry and not something which will, 1 mark, which will probably not guide you too much, not affect you too much in terms of your IB physics scores. Hope that's clear.